This is a very IT-driven industry. Every aspect of the car involves IT. Over the course of a year we do 20 races, so 20 weekends are spent actually competing. The rest of the time, and I really mean the rest of the time because we work sort of 60 hours a week here, we're really just trying to improve the performance of our car. So it's a real R&D outfit that we have here. As Formula One teams go, we're very small. We're around 160 in total. To challenge the big guys, we need to try and work a little bit smarter. So we make a lot of use of IT here. In aerodynamic research, for example, we rely a lot more on computational fluid dynamics, and we have a very large supercomputer here, which replaces a lot of the wind tunnel work that other teams do.
This is the main computing brain behind Marussia. This system is probably the largest single compute environment that's used for management of a single application. This type of computer is approximately equivalent to about 40,000 of your modern PCs, 90,000 iPhones.
There are limits to what we can do with this, and the governing body sets certain regulations, so we would like to do a lot more, but we're limited to running with 40 teraflops of computing power to do this work. Really, a lot of our performance comes from aerodynamics, so that's one of our larger departments with around 40 people in it. One of the ways we try and both shortcut our time to market and to improve our performance is to use CFD. Now, CFD is computational fluid dynamics. It's effectively a digital wind tunnel.
One big difference between the CFD and the wind tunnel is that we have the power to visualize the flow and what it's doing.
We break the car down into around 300 million cells, and we solve the equations that govern the airflow around the car through each one of those cells.
We can see what's going on with the wheel internals. As it becomes more blue, there'll be the lowest pressures. The objectives are to increase the downforce and reduce drag.
From that we can determine the performance, we can develop the car, we can then design the full-size components that go onto the car for the next race. We have to be thinking ahead. And at this time of the year, we're well advanced with our design of our car for next year. And indeed, even for 2014, when there are a lot of new regulations coming in, we're having to study the implications of those regulations and looking at the basic architecture that we need in our future cars. We have an awful lot of data that we acquire every time we run the car. It runs with hundreds of sensors all over the car. During the race, we have a lot of real-time telemetry coming in, so a lot of the data that we're recording is transmitted by radio back to the pits. But we have specialists looking at each aspect, so if someone is responsible for the gearbox, they'll be looking at all the sensors on the gearbox, they'll be looking at the state of health of the car, looking at the performance. So there'll be other people trying to study the tyres, there'll be others working on strategy. Unfortunately, the thing we can't do is we can't send data back to the car, so we can't actually control the car from the pits. What we can do is we can alter our strategies and we can ask the driver to alter certain things. I've been involved in racing now as an engineer for 36 years. IT didn't really exist when I started. A lot of what we were doing was hand calculations, intuitive engineering. And over the years we've built up to these wonderful supercomputers that we're using for aerodynamics. But of course, every aspect of the car involves IT. I would say from the drivers through the engineers and the mechanics, everyone understands the importance of IT in Formula One.